Alright, problem number 6, airplanes and vectors. We're told that an airplane is traveling at a speed of 625 miles per hour and that it's headed directly southeast. Now, directly southeast means that from our north-south, east-west line, it is flying at a 45-degree angle south and east. Both, perfectly split there. So we know that angle. We also know, I'm going to do my vectors in purple. We know that this vector is 625 units would be miles per hour, and that 45 is in degrees. And we are told that a strong wind begins to blow at a speed of 85 miles per hour from the north. So it's blowing from the north and moving to the south. So think of that as a vector on the end of this vector going directly south, and the magnitude of that vector is 85 miles per hour. So we wanted to draw and label a diagram representing this situation. We have our two vectors. Now let's sketch in our resultant vector as well. And I'm going to do that in orange. So it's going to go from our starting point down to the ending point of that composition. And to be consistent, I should have done that 85 in purple. So 85 miles per hour there. Okay, so what do we want to know? We want to know what is the true bearing of this plane. What that means is we want to know what is the value of that angle right there, because that's how we calculate bearings off of the north-south line. And we also know what is the plane's speed with respect to the ground. That's just a fancy way of asking what is the magnitude of that orange line. So pull yourself out of our little vector model here for a moment and recognize that really what we have is a triangle that looks somewhat like that. That's actually a really bad drawing. I'm going to redraw that. So we've got this triangle here, and we should figure out what the value of that angle is. And we can actually do that. So think back to our original diagram. We've got a north-south line there, a north-south line there, and if you can picture that transversal line cutting through it, jump back into geometry. We have alternate interior angles there, so that tells me that up here, that angle is also 45 degrees. Which tells me that linear pair there, that other angle, I'm throwing in some geometry terms, that's going to be 180 minus 45, which is 135, because those angles are supplementary, meaning they add up to 180. So I'm going to mark that as 135. Now that is clearly going to be the largest angle in this triangle, and now I'm going to use the law of cosines to find the side length opposite of that. I'll just call that v for the vector, whatever. So law of cosines says v squared equals 85 squared plus 625 squared minus 2 times 85 times 625 times the cosine of 135. Now, if I take the square root of all of that, I will have v by itself. So plug that big, long, ugly mess into your calculator, and you should get that v, i.e. the true speed of the airplane, is 687.735 miles per hour. So that is the true speed that the plane is traveling with respect to the ground, because it's going to be the resultant of those two forces, because airplanes get pushed around by wind when they fly. So now I'm going to turn my attention to this angle in my triangle, angle that I labeled theta right there. I need to find that angle so that I can find the true bearing of this plane. So I'm going to make this work go smaller now because we don't really need it as much anymore. But think about this. I'm going to label that V side with that value I found, 687.735. Now, since I know that side and the angle opposite from it, and I know this side 85, and I want to find the angle opposite of that, I can use the law of sines. So I'm going to say that sine of theta over the opposite side, 85, equals the sine of 135 divided by its opposite side, 687.735. To solve for sine theta, I'm going to multiply by 85 on both sides, so that would get sine theta by itself. And then to get theta, if I have sine theta, I need to take the inverse sine on both sides. So I'm going to take the inverse sine of that whole thing, and that'll tell me my value for theta. So literally plug that whole thing into your calculator, and you should find that theta is 5.014 degrees. Now, believe it or not, we're still not done, because going back to our original diagram, we know that that whole angle right there is 45, and we just found that small angle, so let's subtract them. 45 minus 5.014 is going to equal 39 point, what, 680? 0.086. I did it backwards, so I said it backwards. 39.086 degrees. So that means that our bearing is south 39.086 east. That is our true bearing, and that 687.735 miles per hour is our true speed. We're done. Now, I do want to also add that this is by no means the only way to solve this problem. You could actually solve this without law of sines and law of cosines. I just think that it's, I don't know, I think it's more straightforward than the other ways. You could set up right triangles and solve this all using right triangles as well. If you can picture extending this up like that, you can make a right triangle and solve it too. Not my preferred way to do it. I like this method, but find a way that works for you. That's your job.